All right, well, if anyone was asleep, I don't think any of you are now. I apologize about that. Well, other than the fact that many of you probably can't hear anymore, I hope everybody is having a good afternoon. Here's it's the same link this time for lecture 18, so you can go and run the script to download the coding assignments that we're going to be doing in lecture today. To give you a preview, the first two problems are going to be a review of developing and solving for the minimum spanning tree of a graph, as well as determining the shortest path using Dijkstra's algorithm. So those two problems are going to be the review. You're going to take 5 minutes to do that. Next thing we're going to do after that is we are going to introduce a new data structure. So we've reached the last major unit of the course this semester. I'll do a brief review of all the data structures we've covered up to this point, and why it is that developing what we're going to call a binary search tree is a good compromise between several different challenges that things like linked lists and max and min heaps and queues and stacks and graphs and all the things we have to consider with searching. And all these challenges, binary search trees are a good compromise, and that's why they're often used in several algorithms that you'll encounter both in the algorithms course, and you'll be able to use several things like this within computer architecture, whether it's cache mapping or an operating system. So things we're going to learn for the rest of the semester are going to be very applicable through the rest of your academic career, as well as through your actual careers once you get to industry. So quick note, for the pre-ternships, the rough draft of your project proposal is due on Monday night at 11:59. I would encourage you to go to this link that I provided here. I go through a step-by-step process of ways in which you can work with your teams to be able to develop a rough draft of a project proposal. I specifically go into ways in which you can take, if your group is in a situation where you have several different potential ideas, or you have an inkling of an idea, how you can take that and do what we're going to call a cerebration session, where you're working with your teams and you're creating a positive environment where you can come up with ideas, propose ideas, especially if you think the idea is bad. I have a little video on there about it's from an author, and he said he learned a lot about creativity from the band Aerosmith. And Aerosmith, every Friday, they had this meeting called Dare to Suck. And the whole idea is that they had required to bring in an idea that you think was terrible, and you had to present it to the group. And most of the time, it actually is a terrible idea. But every once in a while, it produces a couple of #1 hits. And this is a little different than you've probably encountered throughout your academic career. You're given a program, it has to meet some sort of test script, and you meet the results. But what really differentiates you as a computer scientist, computer engineer, electrical engineer, or whatever it is that you're going to be using with the tools you've learned in this class is your ability to creatively apply them in real world situations to be able to make them work together cleanly and safely. So I encourage you to look through that process, get motivated by the videos, work together as a team, and then develop that rough draft. Then after that, you will be reaching out to your project managers. When you reach out to your project managers, they've all done pre-ternships. They're going to walk you through the process of how to fine-tune your proposal, how to make it a realistic project for the last 4 weeks of the semester, be able to suss out things, difference between nice to haves and requirements. And then by Friday, you'll have worked through your team. I'll have read all of the project proposals. You'll email your industry mentor your project proposal. I have another template about how you can email them. You do not require their feedback. Some of them may not have the time to be able to devote to that. But when you do that, you'll then say, all right, we'll come back to you in 4 weeks and we will do our presentation for our final project during the final week of the regular semester before finals week. So that's the general step. I want to point out before we get into doing the problems that I've been getting a lot of emails and calls from industry mentors raving about how well you've been prepared. They're amazed. Wow, they're so well prepared, great questions. You all are doing incredibly well as a team. It's pretty rare to get a call from the CEO of Bell Laboratories raving about your students. But my view, as I said in the lab when we started this, that once they get to see what Notre Dame students have to offer, they'll love you. And that's exactly what's happening. So keep up the good work. I'm excited to see what you all come up with for your project proposals. And on that note, what I would like you to do is that bird's probably yelling at me because of the sound that went off early. we're going to have make problem 1 and make problem 2. So make problem 1 is the minimum spanning tree problem. Make problem 2 is the Dijkstra problem. So please take 5 minutes to work on that. And then after that, I'm going to go to the whiteboard and we're going to work through the solutions to those 2 problems. And then we're going to get started on binary search trees. And as always, please feel free to ask questions and have discussions about your approach to the problem in the course Slack. All right, so first question, problem 1, regarding the minimum spanning tree. I have our adjacency list. For the record, I also have the Slack up here on my phone. So if you have any questions for those of you who are in the Zoom, please feel free to ask them and I can get them while I'm away from the computer. So what is the first step that we need to do when we're setting up a minimum spanning tree algorithm? What are the crucial things we want to keep track of as we're going through it? Yes. Absolutely right. First thing we want to do is we got to keep track of the vertex, the parent, and the weight. So that way, when we get our final minimum spanning tree, we have all the information we need to present the problem. The next question I have is, what is the data structure that we use to be able to keep track of the edges? Yes. Absolutely right, priority queue. So I'm going to put the priority queue here. And so when you're working on a problem like this on the exam, I'm going to show you an example of what I'm talking about. Like I said, very good priority queue in the Slack. You're going to want us to make some space between the edges as they show up. So that way you don't have to do a lot of erasing to keep track of where everything is in the priority queue. And I'll show you what I mean. So the first thing we want to do is the problem states we want to find, and we want to start at vertex 0. So what I would do is I would write up 0, 1, 2, 3, 4, 5, 6, and 7. And I know that the parent and the weight from vertex 0 don't exist. I mean, I'm sorry, that indicates that's our origin. So what are we going to do here? When I put in the edges, what's going to be the final result of the priority queue? Yes. Very good, right? So the way I would do is I would say 0 to 2. Okay, so the other thing I'm going to put visited over here. 0 to 2 has a weight of 4. And then I leave a little space. I'm going to say 0 to 3 has a weight of 5. And then I'll say 0 to 1 has a weight of 6. So right here, this will save you some space when you're working on the exam. You don't have to do excessive erasures. That'll save you a little bit of time. So because 2 to 4 is currently the highest on the priority queue because it has the lowest weight, we're going to say that we're going to visit 2. And then I'm going to say 2's parent is 0. And the current weight to get there is 4. So now what I'm going to do is I'm going to look at 2. And I have 2 edges. I have to 5 with a weight of 7 and to 6 with a weight of 4. So what's going to happen is I'm going to say 2 to 6 has a weight of 4. And this has been removed from the priority queue. And then I'm going to say 2 to 5 with a weight of 7 is down here. And so now, because the outgoing edge 6 has not been visited, I'm going to put this here. I'm going to say 6 parent is currently 2, and it has a current weight of 4. And then we'll remove that from the priority queue. Next, we have 7 and 3. I'm going to put that here. It'll actually be above here, so it would be 6 to 7 with a weight of 3. It's at the top. That's the only outgoing edge. So now I say 7 has been visited. 7's parent is 6, and the current weight is 3. Make sense so far? Right, so 7 doesn't have any outgoing edges, so we don't add anything to the priority queue, which means we now come back to 0, 3, 5. So the benefit of the priority queue is that this allows us to be able to evaluate the shortest weight, the shortest weights first, making it more likely that we won't have to evaluate further on in the algorithm. So now I'm at 3. And now here's the crucial thing. I have 2 and 3, 4 and 4, and 6 and 2. So 3 to 6 is going to be here at the top. Then I'm going to have 3 to 2 with a weight of 3. And then I'm going to have 3 to 4 with a weight of 4. So now this is where we evaluate visited, and this is where we start making decisions. In 3 to 6, 6 has been visited. It's in our visited. So therefore, okay, we don't have any questions in the Slack. So therefore, what we do is we evaluate the current value by weight. Because 3 to 6 is a weight of 2, and 2 to 6 had a weight of 4, this means we're going to update it. So now the new parent becomes 3, and the new weight becomes 2. So by getting that, we have now made it a more minimum spanning tree. But what I was discussing yesterday in lecture was that because we have already evaluated from 6, we are not going to continue the evaluation because we've already evaluated from that particular vertex. So now we can say, well, 3 and 6 is done. I don't have to do anything from outgoing. Now I have 3 and 2. 2 has been visited. So now we just compare the weight. So 2 was initially 0 to 2 with a weight of 4. We now have 3 to 2 with a weight of 3. So now we can beat our previous result and updating it from 3 to 2 with a weight of 3. So now we can remove this. 3 to 4 has a weight of 4. We see that 4 has not been visited. So what we're going to do is we're going to say 4's parent is 3 with a weight of 4. And then we're going to mark 4 as visited and remove this from the priority queue. So now we look at 7 and 5. So it goes to 7 with a weight of 5. So we're going to add this. Now, in the tie break situation, just put it below. 4 to 7 with a weight of 5. But what we're going to eventually see is that because the weight is already lower, it's not going to be replaced. So what's going to end up happening is we're going to do 0 to 3. So now we're going to evaluate from 3. 3's already been visited, my apologies. So with 0 to 3 is a weight of 5. The current path to 5, I apologize, I left it out somewhere. If we're doing 0 to 3, the current weight is 0 to 3 with a weight of 5. And then we're going to evaluate from 3 now. So we have 2, 3, 4, 4, and 6, 2, which we've already evaluated. So now we can remove that. And by the way, I'm going to put this there because I feel like I've made a slight mistake, but I'll check it because I have the correct answer up there on the podium. But now what I'm going to do is I'm going to say 4 to 7 with a weight of 5. We can't beat that, so we're going to remove this. And now we're going to go our 0 and 1. So by doing this, we can ensure that if it's a connected graph, and I promise you on the exam it will be, that you'll be able to visit every single vertex. So here we go to 1. We list that 1 is visited. So 1's parent is 0 with a weight of 6. We go to here, 1 has an outgoing edge to 2 with a weight of 5. So now that's in the priority queue. We have outgoing edge to 4 with a weight of 3, so that's actually higher. And then we have 1 to 5 with a weight of 6. So now let's start evaluating. We look at edge 4. 4 comes to 3 and has a weight of 4. We see that this is lower, so we replace this with 1 and 3. We've already evaluated 4, so we don't need to do that. Now we're looking at 1, 2, and 5. We see that 2 has 3 and 3, which has a lower weight. So we remove that. And I already removed 0 and 1. So now I'm looking at 1 and 5. 1 and 5 has a weight of 6. 5 has not been visited. So that's parent is 1 with a weight of 5. So now let's evaluate 5. We have 4 and 2. We have 5 and 6 with a weight of 5. And then we have 5 to 7 with a weight of 4. Okay. Does anybody have any questions so far? And so from there, when we continue to follow the rest of the algorithm, it's going to look like this. So let me show you the first solution. And I see there's a question in the Slack. The question is, when you visited 2, you put the next option. Why did you not do the, never mind, it's because of the weight. All right. So I see there's another question being typed up. What I'm going to show you here is the solution. Okay, so everybody see that? All right, so this is what the graph we're going to show here represents. And so this is the full graph, and this is the full adjacency list. And then here, I'm going to zoom out just a little bit. This is the final minimum spanning tree. So we've reduced everything, and this is the final result, and choice B is the solution. And so I saw there's a question being typed up in the Slack. Should 5 with a 1 have a parent 1 have a weight of 6? So initially, that's where it was here, but we're eventually going to solve it. And that's going to be its actual parent in the adjacency list. So 1 is here. I represent that as B, and F is 5. So we see that that remains in the vertex. Right. So Natalie, please let me know if that addressed your question. Does anybody in here have any questions? All right, so the second question, we're doing the same thing, except we're doing Dijkstra's algorithm. So let me go back over to the board. I'm going to quickly go over, board left, your left. And And I'm going to quickly go over the solution here. Actually, I'm going to do you one better. I'm just going to stick here and produce this result. So what happened is that when we go through, this shows the actual process with the stack. So we start out at 0 and 1, and we're going to put 1, 2, and 3 on the stack, like we discussed yesterday. And then we start putting in those weights. Those weights would be 6, 4, and 3. And we work through that process of iterating through, using the stack to be able to update the parents and the weights. And so the way I would do this on an exam is that I would give you the adjacency list, and you'll be given a few minutes to be able to walk through and prepare that particular problem. Did anybody have any, would anybody like me to address any questions regarding the Dijkstra's algorithm before I start in with the regular topic for the lecture today? Let me check down the Slack as well. Okay. And so I believe the choice was E for problem 2. And so if you work through this, I will share my screen here. And what we will see is that for this problem here, this choice was B. That's correct. And so you make problem 2. And I believe, yeah, 130367 is the correct answer. So that's E. And if you look there, you'll see prob 1 and prob 2 text indicating that you've completed those problems. All right, so what I would like to do next is I would like to discuss some compromises that we have to make. So until this point, we've used our data structures to be able to address specific tasks. First, we went over object-oriented programming. We went over encapsulation, abstraction, inheritance, and polymorphism. You're working on inheritance and polymorphism now in the coding challenge that's due tonight. The next thing, we started talking about the stack and the heap and the registers and how we use pointers to be able to allocate memory. And we use just the memory we need for a singly linked list. And then we overcame some of the challenges we found with singly linked lists with doubly linked lists. But the crucial thing is that if we wanted to see if an element is in the list, we had to do it in big O of n time. So then we came up with this idea of hash tables. We can allocate a lot of memory, but then using a hash function, we can find something in an amortized big O of 1 runtime. Then to try to find some compromises, we initially started talking about max and min heaps. Max and min heaps, we tried to get around pointers, connecting the values by using a dynamic array, which is what J.W.J. Williams, the inventor, wanted to do. And then we started talking about, all right, well, these graphs can have these massive interconnected values. We also discussed if we're trying to search, we have to do big O of V plus E. And we did that when we were doing breadth first search and depth first search. We tried to reduce the complexity by using minimum spanning trees or topological sorts. Furthermore, if we have a dynamic array, we would have some sort of quick sort or bucket sort as you did in coding challenge 5. And furthermore, we have also worked on, you did a sorted doubly linked list to make your first priority queue in coding challenge 4. And also we went over heap sort for priority queues. So here's an interesting challenge, finding a value in a low memory environment. So when we have hash tables, we'll start with linked lists. So linked lists are good at connecting everything, but we want to be able to find an element fast in a low memory environment. What is the drawback of a linked list in this environment? Somebody want to take a stab at it? Yes. Absolutely. We don't have direct access. We have to iterate through. So therefore, we have a big O of n search time. And if we want to sort it, it becomes big O of n squared. So what's the drawback if we're trying to go the other way? We want to say we've got this amortized big O of 1 runtime with a hash table, and we saw that there's a worst case linear probe with big O of n, so we overcome it with quadratic probe and double hashing. But still, what is the big issue here if I'm trying to implement finding something fast in a low memory environment? Yes. Hash tables take a relatively lot of memory compared to a linked list, especially as the type or class that we're templating the values to gets much larger, and that dominates as opposed to the pointers. Furthermore, when we're trying to iterate through the underlying dynamic array in a hash table, they are not in any kind of sorted order. So it doesn't help us in that particular way. So in 1960, we have what are known as drum memories. And while drum memories only have about, at this particular time, like 20 kilobytes in memory, a lot of the principles that were led to first implementation of a binary search tree still apply today, whether it's an Internet of Things, where you have several sensors, low memory applications. You're trying to reduce the power consumption with a little bit of trade-off in runtime, but you're getting a significant benefit in memory. And we want to be able to do searching and try to find this result. Hash tables were first implemented the year before by trying to look up keywords in context. However, if you're trying to sort something, they weren't terribly useful, which is what motivated the idea of a binary search tree. So we need to sort, but we need to do it in faster than n squared. So ideally, n log n. We need to be able to find it, but we have to find it faster than the linked list's big O of n. And we need to reduce memory, so we're getting that trade-off from the hash table. So to do this, we are going to introduce the idea of a binary search tree. We're going to say that a binary search tree is a linked data structure where each node contains one or more child, or what we're going to call them, leaf nodes. The ones we're going to study first, binary search trees, have two. Before, with the doubly linked list, we had a previous and next, so we've actually coded something very similar, but instead, they're both going to go out. In a binary search tree, we're going to typically call them left and right because we're going to use the structure to help sort. So what I want to do is, we have an example where we have insert 30, 20, 25, 40, 50, 35, and 10. So what I want to do is I want to quickly work together as a class and see what it is. I'm going to insert the first two, and then I want to see you all tell me where it is that the next value should go. So the first one is 30. That's what we're going to call the root node. And then the next value is going to be 20. 20 is less than 30, so we're going to make it go to the left. So that will end up over here. So the way it works is we make decisions left and right. Right is bigger. Okay, your right, my left is bigger. Left is smaller. So we went to the left for 20. So where do you think 25 is going to go? Who wants to tell me where they think 25 is going to go? Yes. To the right of 20, absolutely right. So it'll end up here. All right, what about 40? Where's 40 going to go? Yes. Very good. All right, and what about 50? Absolutely right. And what about 35? Who wants to tell me 35? I saw some hands up here. Yes. Oh, nope, somebody's just scratching their head. Where should 35 go? Let me see if anybody's telling me in the Slack. All right, we do see some answers in the Slack. To the left of, to the left of 40 is absolutely right, Sebastian. And where's 10 going to go? Everybody, tell me where 10 is going to go. Outstanding, thank you. So we now have a good sort. And so what I want to do is we're going to build the foundations of binary search tree. We're going to build a binary search tree node just like we did with a singly linked list and doubly linked list. So please go to the include folder to file binary search tree 1. And what we're going to do is we're going to see the foundations. So this will be binary search tree node 1. This is the file that I want you to open. And so it'll say problem 3 starts here. So a struct, by definition, everything is public. So therefore, we're going to use this inside of our eventual binary search tree. So we have 3 values that we're going to allocate. We're going to allocate the data itself. We're going to allocate a left pointer, and then we're going to allocate a right pointer. So we're going to start with T data. So let me zoom in a little bit so that way everybody can see. And then we're going to say binary search tree node, template pointer. I'm going to call this one left. And I'm going to say binary search tree node, T star right. I'm going to write two constructors. The first one's going to be a default constructor, and another one we're going to take in a value for the data. So what do I need to do? What is the ordering that I need to put in for the member initialization list when I do the constructor? Yes. Absolutely right. We're going to do data left and right because that's the order that's going to be allocated on the data heap. And outstanding, very good. So we're going to say node, BST node. And now we're going to make our member initialization list. So data, that will default to the default constructor of that templated type. And then we're going to say left is going to be initially null. And that null keyword is permitted because of this C standard library that we've included here. And likewise, we're going to do right, null. All right, so I want to ask, since this is something I see in office hours recently, and this maybe will help you on the coding challenge, what do I need to do for a constructor and a destructor after I put the member initialization list here? Yes. Absolutely right. C++ is a bracket procedure language, and Lydia, outstanding. I see you got that right on the Slack as well. We put that there. The next thing we're going to do is we're going to call in a data type. So we're going to read in BST node. And what should I put for the input? What are the crucial things? So it's going to be T data in, but what else do I need to have there? What have we been doing all semester long on this? Yes. Absolutely right. We're going to do const, and then we're going to do T, and then we're going to do call by reference with the ampersand. So I'm going to say data in. And then it's the same thing, except instead of data with blank, we're going to have data in into the member initialization list. Right, does anybody have any questions about this so far? And so this is kind of the simple part. So what I would like you to do is I'd like you to save it and upload it to the Notre Dame machine. And I'm going to show you what is in test BST node 1. Right now, we're not allocating any memory. So therefore, we do not need to include the destructor, operator, and copy constructor yet. But we will do that soon. Here, I'm creating two binary search tree nodes, M, B, and R. And then what I'm doing here is point left, because it's a struct, dot left, I'm sending that to ampersand node 2, which means the base address of node 2 on the data heap. And we're doing the same thing for node 3. And then I'm printing the first value, and then I'm printing out the left child and the right child. So what's going to do, it's going to print out M, and then it's going to print out B, and then it's going to print out R. So you have this working, and it's been updated. You can run make test BST node 1, and it will compile, and you'll see that M, B, and R. And if you have that done correctly, you'll have the problem 3 run output to indicate that you've completed the problem. So while you're all doing that, I'll put the code back up, and then I'll talk about the next steps while you are finishing. So the crucial thing is, right now we haven't allocated memory, but we're going to need to. Does anybody remember from back when we did singly linked lists and doubly linked lists, what the challenge was when we just had nodes and we were allocating them in main, but then connecting them with the destructor? Does anybody remember the big issue that we came across? Yes. Absolutely right. We got the memory trace error because we had a double free, and we're going to reproduce that same error next. Okay, so does everybody have this code? So what I'm going to do in BST node is I now have the constructor, the overloaded constructor, and for now I just have a destructor. And now I have a copy constructor where I copy the piece of data, and then I have left and right are null. And then I have the assignment operator where we first check to make sure they're not pointing at the same address, and then I assign the data. And so in test BST2 node, what's going to happen is I have the same thing, except now I'm using the new keyword. And because I have that assignment operator in there, I'm able to make this code work. And then I say node left and node right data. I'm going to print it out. And then I say deliberate segmentation fault here, node 1 left data. So let me bring up, so I have MB and R. So what is this line of code where I have the deliberate segmentation fault? What is that actually asking for? So node 1 is M. Yes. It would be the left child of B, absolutely right, which doesn't exist. Since we don't have any allocated memory there and we're requesting the data, that's where we're going to get a segmentation fault. So let me clear all drawings. So I'm going to run this compilation. I'm going to say make test BST node 2. And we're going to see that's going to work, but it's going to seg fault. So one crucial thing, when you're working with binary search trees, you're working with trees in general, and we're now really digging into pointers, make sure the first thing you do before you do any operation, and we're going to do this today when we do insertion, check to ensure that what you're trying to do actually has been allocated to our program. If it's null, that means we have reached the end of what we're going to do, and we might have to, we're going to see when we work into traversals that that's going to be helpful for us. You don't want to try to allocate data to a node that doesn't exist. So this is a crucial thing, and I will show you where I apply that design methodology when we get to insert. And so the next thing with BST node 3, I now have a destructor. So what I've done here, let me skip through on the slides a little bit. Okay, we see that that's a segmentation fault. And so what we need to do when we're doing with the destructor is we need to eventually clean all the memory off of the data heap. So we actually need to run a destructor. And what I'm going to do is I'm going to do the same process that we did for a linked list. So remember when with a linked list, I called delete head, and then I kept calling delete next. And then when we got to the end, it recursively freed everything. We're going to do the same process, but what we're going to do is we have to go in both directions. And we have to make sure that we free the elements to the right, to the left, and then myself. And the reason why we have to do that is if we free this first, we can't get to those other elements, and we end up losing memory. And so the way we do this is, in this case, I'm going to go to the right. If I say the right is not null, so there's the first example of what I was just talking about. First, we check to make sure that your right over here actually exists. So then I'll try to call the delete, which will then go to that node, and then try to call those deletions. Then we go to the left. And you can do it in either direction. In this case, I'm just choosing this because it'll tie in well with something we're going to do later called a post-order traversal. But the crucial thing is that this allows us to be able to delete things in an order that we don't lose the memory. In this code, I've also included this, just like we did with the, does anybody have any questions on that before I continue? All right, so remember I did the exact same thing in the linked list where I created an overloaded assignment operator specifically for the node pointer. So the previous one is I'm making a copy of the actual node using the assignment operator, whereas now I'm just saying I want the pointer. And this helps us by saying, all right, we have a register that contains the base location of the address on the data heap, and we refer to that in C++ as this. Based on that, that's pointing to that allocated memory. I'll show you an animation in a little bit. I set the data inside this equal to the address of assign. So now the two pointers are pointing at the same location in memory. And then I return that. Yes? Well, assign is already a pointer. That's a good question. Because, yeah, that's absolutely right. Very good. Thank you. Appreciate that, catching that, Nikita. So now we're pointing to the same location because the address, the data inside the pointer of a sign is equal to the data inside of this. So now we're going to write functions to be able to help us insert and print the values. When we do insertion, we're going to do the same process that you all use to figure out the location in the animation. And the next thing we're going to do is we're going to figure out how to actually print it and what we're going to call an in-order traversal. So what I would like you to do is go to source test bst node 3.cpp. And so you will see at the top that it will say problem 4 starts here. So the first thing we're going to do is we are going to write up a method to actually insert a node. And so we want to be able to do it for anything, because what we're going to do here with the BST node, we're going to apply the same ideas, and we're going to eventually encapsulate them within the class. And so the first thing I want you to do is I want you to do template class T, and this method we're going to use is called void insert node. And we're going to pass 2 different elements to it, and I'm going to ask you why you think I did something here. So I have BST node and then ampersand, cur pointer. And then the second one, BST node, and this is just going to be a pointer, insert pointer. Bless you. So before we do anything else, what is the difference between those 2 pointers inside the function call? What am I doing differently with those 2 pointers? Any ideas? Yes. The first one is called by reference, and the second one, what is it? Is it passed by value or is it passed by reference? I want the value that the pointer is pointing to. In C and C++, so for those of you in systems, you're now working on C, you have to dereference the pointer, right? When you dereference the pointer, that's passing by reference because we actually have a reference that we're pointing to, and then we dereference it to do that pointer arithmetic for us. But if I'm passing the value where it's pointing, and I don't dereference it, and I want that value itself, what is that? Is that passed by value or passed by reference? Yes. It is passed by value. Very good. So what I'm doing is I'm passing by value a pointer, and I'm calling this cur pointer by reference. And so, in fact, what I want to do is I want that pointer, that's the location. I've allocated a piece of memory on the data heap, and now I want whatever the cur pointer is when I eventually get to a specific location to eventually point to that same place. So now we're going to use the recursion to be able to do this work. So the first thing, what was the, I mentioned it a couple of times now, what's the first thing you should do when you're working with pointers before you do anything else? Yes. Check to make sure it's null, outstanding. So then we're going to do that with cur pointer first. If cur pointer equals null, and it turns out this is where we're going to want to do the work. So let me scroll down a little bit so everybody can see. Once we find a null pointer, now we're going to change the value it's pointing to insert pointer. So we're going to say cur pointer equals insert pointer. And then we're going to return. And so what we're going to see for the rest of the code in this particular function is we're going to traverse using our knowledge of the data to get down to a specific pointer, null pointer. So it's the 2 null pointers going off of a leaf. And when we find the right one, we're going to use that and insert the node in the tree there. So on that point, the next thing we need to do after this, we're going to say, well, if the data in the current pointer is greater than the data in insert pointer, so the current pointer is greater, so I want to insert, current pointer's already here, insert pointer's here, current pointer is bigger, which way do I want to go? I'm using your direction, so your left or your right. If it's bigger in the currently existing value. So let's say I had 25 and I'm inserting 10. Which way do I want to go? Left, outstanding. I see a lot to the left, right? So now we're going to say, if the current pointer data, so we have to dereference, is greater than insert pointer data, if that happens, we're going to recursively call insert node, except this time we're going to use cur pointer left, as you all correctly figured out, and we're going to keep insert pointer the same. Next thing we're going to do is do the opposite. If cur data is less than, so I apologize, this should be else if. And this time, if it's less than, I want to go to the right. So we're going to replace that with right. And so while you're typing that out, I'm going to describe the last thing. For this particular tree in our example, we are going to assume that there are no duplicates in the tree, that if we find something, we leave it alone. So just to drive that point home, in theory, you could just leave the code as is. What I'm going to do to emphasize and help make clear the design of this particular tree, I'm just going to say else, and I'm going to say data is the same, do nothing. Okay. Does anybody have any questions about this before I continue? All right, let me also check the Slack and the chat. I don't see any questions in the Slack, and I don't see any questions in the chat either. So here's the code that's going to go up. What I'm going to do really quickly is I'm going to upload it to the Notre Dame machines and compile. And we're going to do make test BST node 3. And here's what's going on in the rest of test BST node 3. So I'll come back to this so you all can finish up in a moment. What's going on in main is I create 9 nodes, and then I use the insert node method. I pass this new root node. I create a pointer and set it to null. And then I'm passing the root pointer and then the address of each node pointer, and we go through following those directions until we've inserted all of the nodes. And then I'm going to call print tree, which is what we're going to write next. So in print tree, we are going to do what's known as an in-order traversal. So an in-order traversal means I go to the left, I find the smallest value, the middle value is the next largest value, and then right is the largest value after that. So if I have a small one, so if we had, let me annotate here, there we go. If I had a small one, if I had F, A, and Q, right? The way it'll work is I'll go here, and if I have a valid place to go, I start here, and then I print A. Both of these are null, so I don't go any further. I would come back up to the middle, I would print F, then I would go to Q. Both of these are null. So I would print A, F, Q. So this is our goal in printing this out, and we call this an in-order traversal. So what I'd like you do is go above main. So would anybody like this up any further? All right, please take a split second. I'm going to scroll down to the else if, so that way that's at the top, and then I'm going to start here with our print. So when we print, we're going to template again, say class T, and I'm going to say void print tree. And this time, I'm passing const BST node, template pointer, and I'm going to call this cur pointer again. So what's my rule? What's the first thing I want to check before I do anything else? Very good. Check to see if it's null. So if cur pointer is equal to null, just return. So now I want to go left. So what I'm going to do is I'm going to recursively call print tree left. And I'm going to say cur pointer left. And then, I'm sorry, let me scroll up just a little further. There we go. And then what I'm going to do, and just to review, I have my cout endl over here. So I can use our compiler directive cout to print out the data that we're currently at. So it's going to be current pointer data. Right? Then leave a space. I have the enter in main. So that way it's all on one line. And so if I've gone left and I've printed out the value, what's the last thing you think I should do here? What do you think I should guess? Yes. Yeah, we're going to recurse to the right. Outstanding. So that is what we're going to do here. I'll put that here and we'll do right. And so that's the entire tree that we're going to use to print. So it's going to print out, but then, as was correctly predicted earlier, we're going to get our memory map trace because I have that destructor, and I'm going to go over an animation and show you what's actually happening at the different levels of abstraction, at the algorithmic code, and in the architectural level. So let's save and compile, see if I typed everything out right. And you'll be able to run make test BST node 3. And we see that it runs, and as we predicted, it has generated our memory map trace. But also we see here A, B, C, D, F, M, N, R, and S. So we have successfully printed them in order. And if you've done that, you'll also see prob4 text there. Does anybody have any quick questions before I go into detail about precisely what's happening as a data structures concept? Oh, did you have a question? Oh, you're just scratching your head. All right. So let me go into the animation. So there's the code. And here's what we were expecting. And that's what we got. And so let me move this over here. So we start out in main. We allocate some code onto the data stack. And then what's going to happen is we allocate M, and that allocates the memory. And we do the same thing with node 2, node 3, and node 4. And it's just as a reminder, those spaces in between the registers and the code, that's there for ease of reading. That's not necessarily how it will actually be allocated in the memory. So now what I'm going to do is when I create that binary search tree node char star root, basically, I'm setting it equal to null. That's the data inside the register. Remember, node BST template star is the same thing as a void pointer. It just adds context at the operating system's level. So the next thing I'm going to do is I will insert the node where I call root and the address of node 1. So now what that's going to do is that's going to call insert node. So first I'll say, well, if cur pointer is equal to null, and that's root, we see that it is. It's not pointing to anything. So now I'm going to say cur pointer is equal to insert pointer, and we now see that the root is going to point to M. And does anybody have any questions on that? There is a question. Why does current pointer have to have star ampersand? So that's the call by reference. So what's going on here is because I have call by reference and I have another call on the instruction stack, I want to actually change the value here in this register. So by calling it by reference, I can update the value. So before, I'll go to previous animation here. You see how it's not pointing to anything? Because I call it by reference, I can update it and it will preserve the change. If I didn't have that there and we propagated it up, you would actually print out inside the function that it worked. And if you're trying to troubleshoot and try to figure out why your tree isn't constructing. But then when you went outside that call and that call is removed from the instruction stack, you lose the scope and therefore you lose track of the tree. So WebHop, let me know if that addressed your question. So let me continue. We returned, and now I'm going to add node 2. So now we do the same thing. Root is not pointing to null. So now I'm going to say, well, what's the data pointing to? M is comparing with data 2. So that's M and B. So M is greater than B. So we're going to call left. And when that passes, and I see, I'm glad to hear that addressed your question. When we recursively call, we're going to make another call onto the stack. And now we're going to evaluate BST node left in that particular node on the stack. We see that it is, in fact, not pointing to anything. So now it's going to update. And we see that it's now pointing, just like we did with a doubly linked list, it's now pointing to another location on the stack. And it's pointing to the base address of that node. And we're going to do the same thing with node 3. We're going to recursively go through. And node 3 is R. So this test isn't going to pass. This one will, because R is greater than M. So we're going to recurse to the right. And we see that right is now null. So now we're going to set right equal to that node. You see how we have the straight data heap, but now we're doing this to create physically the binary search tree. And then we're going to do one last one here. We're going to insert A. So A is smaller than M. So we call it that way. A is smaller than B. So that's going to take us this way. And now we're at BST, the left one for B. That one is null. So we now see that that points to A. So that's how we match the architectural level, the algorithmic level, and the data structures level with the code. Now, does anybody have any questions about this so far? I'm going to show you exactly where the memory map happens. And this is going to motivate how we're going to write code for the rest of the semester for trees. I don't see anything in the Slack either. And so what's going to happen is, recall that the C++ destructs in the opposite order. But I want to show you something funny that happened in memory map. In the memory map, when I run make test BST node 4, it's the same thing except I'm printing the value of this. So actually, let me vim real quick. Actually, I don't even need to vim. In BST node 4, it's the exact same code, but I'm printing out constructing this. And here in the overloaded constructor, and here I'm printing out destructing this. So when I run this, make test BST node 4, and I go to where everything was being constructed, we see that it prints everything out. It ends at 3 foxtrot 0, and it starts at 3 foxtrot 0 and goes to 3 delta 0. But we expect it to go to B, but it actually prints out 3F0 again. Does anybody have any theories as to why that is? I don't see any hands up. Dare to suck. I'm not going to judge you. There's only 2 days in the semester I have to, right? Today's not one of them. Someone give me a guess. What do you think is actually going on there? Why it's not destructing in the same order like we learned with linked lists? Yes. Yes. Mm-hmm. Perfect answer. It's almost like it was from my slides, but outstanding job. It's constructing lower in the tree because that's where we start low, and then it moves up. So great job on deriving the right answer. So now let's look at it in the animation. And sorry, that meant to come off as more of a compliment. That was like, it was like you're smart, not that I thought you were like reading ahead. So here we have constructed and destructed order. Then it gets cleared, just like we predicted. Then we go to 40, and now we're going to try to delete left first, which means we're going to try to go to that last location. So we delete 40, and then what's going to happen is when we try to delete 20, 20 is going to try to delete left first, which means left was 60. But they don't match because we forgot to tell the operating system, we forgot to tell that particular scope that we already freed that memory and given it up. So it says, wait a minute, double free, you tried freeing it again, and now I'm going to throw all this memory information at you to try to help you figure out what happened. So that's what that big memory dump is. So we fix that with linked lists by doing encapsulation. So what I want to show you for the last few minutes of lecture is how we're going to take that code that we put in the binary search tree node, as well as the insert method and the print method, to be able to produce those results in encapsulation. So first, let me go inside include bst1.h. There's a fair amount of code, so I want to break it down. And we see that we have the root pointer, and then we have the constructor, where it's just going to construct the root, and inside BST, it's going to call delete root, which, as we're going to see, is going to delete left and right by calling the binary search tree node destructors. So now that I've broken this down, I would like to show you the rest of the code. So I have the copy constructor. Actually, I'm not going to show you copy constructor yet. We have to figure out a way to copy the entire tree. And so we've learned about post-order traversal, which we're eventually going to use to delete. We're going to learn about in-order traversal, so we actually know the sorted order of the tree. But now we're going to cover what's known as a pre-order traversal. And a pre-order traversal is the ordering of data in which if you insert it into the tree in this order, you will get the exact same order of an already constructed tree. So for example, I have this. If I were to insert into a different order, I would get a different tree. So in order to get this, I'd have to say, well, I'm going to insert 15 first, so I know it's at the root. And then, well, I would want to insert 10. If I want to insert 6, so that way I know 6 is to the left of 10. Then I want to do 12. Then I want to do 25. Then I do 18. And then I do 30. So does anybody see the ordering there? What the pre-order traversal would be? So post-order traversal was right, left, middle, and in order was left, middle, right. What do we think pre-order is? Any guesses? Yes, hand up. Oh no, you're just scratching your head. Any ideas? Go ahead. Right, middle, left. Outstanding. So we want to do middle, then left, and then right. Sorry about that, Lydia. You were talking about the other one. So here's the way it will work. We're going to do copy tree. Destin node, this piece of code here. So first we're going to do middle. So we're going to say 15. We're going to create 15, and then we will recursively go to the left. And then we get 10. We go to the left, and we're updating the pointers each time, and then we get 6. We now found that it's null for both children of 6, and that's going to go up. So now we're at the right, but this is at the recursive call for 10. So 10 is going to go down, and that's where we insert 12. Does that make sense? So it's going to be middle, left. We go all the way to the left, and then we're going to go all the way to the right. And so I'm going to continue the animation all the way through. And so now 25, 30 children are both false. So now I can use this copy tree method that I just presented to be able to first allocate the root value, and then I'm going to copy the tree using that data. So I can use this both with a copy constructor and an assignment operator. So the only difference here is that if this is not equal to the address of assign, we are going to be able to, first we check to make sure they're not the exact same node so we don't do redundant work, and then we copy everything over using the copy tree method. So, okay, I apologize. I thought I had deleted these particular slides. Let me click through. Okay, so post order, we've learned it's right, left, and middle. So we get rid of 25. Then we get rid of, we get rid of 30. Then we would get rid of 25. So we see that's 30 and 25, and that's going to go to the left. But then it's going to immediately go to the right again. So the next one, which value do we think is going to be next for the post order traversal? Yes, in the back. 12, outstanding. That's exactly correct. So we're going to go to the 12. Sorry about that. So 12 is gone. We then go to the left, so it's 6, 10, and 15. And so what I'd like to show you next within BST node 1 is the different ones for printing in order. Oh, that's why that's happening. I'm really coming for your ears today. I apologize for that. So in order, I'm going to say first thing, just like before, cur null is equal to null. Then I'm going to go left. Then I'm going to print the current value, and then I'm going to go right. So that's the in order traversal. Pre-order, I'm going to print the value. Then I'm going to go left, and then I'm going to go right. Then in post order, I'm going to go right. Then I'm going to go left, and then I'm going to print that value. And then I call all three of those in a friend operator. So when I call the friend operator, when I want to print the tree, it'll print the in-order traversal, the pre-order traversal, and the post-order traversal. And so what I would like you to do, well, actually, I'm going to run make test bst1. And we see that it prints out 3 different trees. I'm going to show you what this code does, because this will allow you to see how we've tested it. So I have a tree, just the tree. And we have M, B, and D. And then I create 2 other trees. The first one, I use the copy constructor. Tree 2 calls the tree. And tree 3 uses the assignment operator to create the tree. So now I have 3 different trees with the same pieces of data, but the crucial thing is that there should be 3 different copies. And I can prove this by doing insertions into the different trees. So I insert A into tree 2, and I insert Z into tree 3. Tree 1 should not have A or Z. Tree 2 should not have Z, and tree 3 should not have A. So if we've done that correctly, that means we have done our appropriate use of in-order and pre-order, allocation with the assignment operators. And we see here that the first tree only has the 3 values. We print them in order. The pre-order, we know that's M, B, and D, so it worked out correctly. In post-order, we want to delete D first, then B first, and then M. We see that we've added A correctly into tree 2. We see that we've added Z correctly into tree 3. So now we have a correct assignment operator. We have our correct copy constructor. We have the same destructor that we wrote before. And because we've encapsulated it and we're only deleting through the root, we've managed to preserve the memory mapping. Okay, and so there's the results here. So what I would like you to do is I want you to take the next 3 minutes, and I want you to work on problems 5 and 6. Problem 5 and 6 use the binary search tree that is up on the screen. And the 2 questions are going to be find the pre-order, select which one is the post-order. So I'm going to give you 3 minutes, and then we will go over the solution together. All right, so let's work together first on the pre-order traversal. So where do we start with the pre-order traversal? What's the first value that we're going to see? Yes, 20, outstanding. So we start here, and so I'm going to write the pre-order traversal here. So 20 is the first one, and then which way do I go? Left, very good. So we go here, and then which one do I print next? Left. So we want to print 10. Remember, this is pre-order. I want to get this in the exact order. If I insert 20, I insert 10, I'll get the exact same tree. So which one do I want to print next? 7, very good. Next one. 5, very good. Which one? Next one. Next one. 9, next one. Very good. Which next one? 15, next one. Next one. Next one. 30, very good. All right, that's where most students will trip up right here. Next one. 25, very good. Next one. 22, next one. And last but certainly not least, 35, very good. I believe that's choice B. Post-order traversal. What's the first one I do? Yes, in the back. 35, outstanding. Now what's the next one? 24, very good. We want to go down here. We got 24. Next one. 22, next one. 25, next one. All right, this is the big one where students get tripped up. What's the next one? Outstanding, 17. Next one. Next one. Next one. Next one. Come on, we're almost done with lecture. We do 9. Next one. 6. Next one. 3 to go. Outstanding. Good job. All right, let me check to see on the phone if there's any questions in the Slack. There are not. Does anybody have any questions about this? All right, so let me go back up here and describe what we're going to start on next week, and then we'll finish everything up here. So I'm going to go to lecture. All right, so what we're going to do next week, we are going to finish up binary search trees. We're going to discuss methods, find minimum and find maximum. We're going to go into detail about deletion, and then we're going to discuss a challenge that comes up with a binary search tree. So specifically, let me draw it up to get you thinking about things that we need to do in the future. So what happens if I insert everything in order? What happens if I do 1? If I insert 2, where's it going to go? All right, very good. What about 3? 4, 5, and so on. So what ends up happening is this becomes a glorified singly linked list with an extra pointer that's all pointing to null. So what we're going to start working on are known as balancing mechanisms. So we will take advantage of inheritance and polymorphism to build what is known as an Avl tree. And it's a data structure that you will revisit over and over again in your algorithms course because it has a fixed, guaranteed, big O, n log n insertion for n elements, log n search time, and so on. And then we're going to talk about the challenges with that. And then we're going to use that to develop a B tree. And then the week after that, we will devote an entire week to a specific data structure called a red-black tree. Before I dismiss you, does anybody have any last questions? So make sure when you have problem 5 and problem 6, run the script. I believe it's 135 points towards your in-class coding assignment. And if there are no other questions, you are dismissed. Have a good weekend.